our final video on the beginning parts of rotational dynamics is going to be looking at gravitational potential energy, above the Earth's surface and escape velocity and some Kepler's laws. So let's get started. So if I have this satellite located 150 kilometers above the Earth, I can't just say gravitational potential energy equals mgh. Okay, and it's because the g is no longer 9.8 as we get farther and farther away. So instead we use the equation, gravitational potential energy, okay, is equal to g, and again I'll use capital M for this guy since it's so big and a little m for that. So it will be big M, little m, okay, divided by r. It comes from taking the integral of the first equation, the Newtonian law equation. So we're taking essentially the integral of 1 over r squared, and we're left with 1 over r when we're done. So I can calculate the gravitational potential energy at this location, just by plugging in the mass of the Earth, okay, the mass of the satellite, multiplying by the g constant, and then multiplying or dividing by r. Now, if I want to know how much work it takes to go from this location here to another location here, okay, let's just draw an x for it. And then what I can do is just use this equation one more time at my new radius, and then just take the difference. So the difference between the gravitational potential energies is going to be how much work it takes to move it farther away from the Earth. Of course, if it goes closer to the Earth, that'll be a natural thing because it's attracted to the Earth. So we just use this equation to get our gravitational potential energy. Now, what if we want to escape the Earth? Okay, so the only true location where gravitational potential energy is equal to 0. So gravitational potential energy, okay, approaches 0 when the radius approaches infinity, right? So if I want to calculate, okay, the escape velocity, okay, from any planet, I'm going to set kinetic energy equal to gravitational potential energy. Because what's going to happen is whatever velocity I have to escape from the Earth, I need to use it all up and convert it all into GPE, and we want to be infinitely far away when we're done. So it goes like this. We have 1/2 mv squared is equal to g big M little m divided by r. Okay, and once again I see little m's cross off. Okay, so velocity, and this is going to be escape, so I'll label ESC so that we can just, so that's going to equal then the square root. This 2 is going to go to the other side, so it's going to be 2 g big M and all divided by r under the square root. So very similar to our orbital velocity equation, okay, but it'll be just a little bit different, this number 2 here. So m is the mass of your planet, r is the radius of your planet, just from here to there. So I'm going to specialize this and just say radius of the Earth. Okay, and g, of course, is our gravity constant. Okay, now we're going to finish up with Kepler's laws. Okay, there are 3 of them, and it's to observe the path of planets around our sun in the solar system. So rule number 1, planets orbit the sun as ellipse, and with the sun at one focal point and then empty space for the other. And they do this elliptical orbit because the gravity of the other planets draw them out into these elliptical orbits. A line drawn from the sun to any planet sweeps out equal areas and equal time intervals. And that's really a conservation of angular momentum going on there that we'll be talking about in our next set of videos. And the square of the orbital period is proportional to the cube of the average distance from the planet to the sun. Okay, so let's take a look at that, those 3 laws. So the elliptical orbit, I think, is self-explanatory. Okay, now what about those equal areas? So I'm going to choose some lines to draw here. So let's say our planet, okay, is going to move in a certain time interval from here to right here. So we're just going to let some time go by and let it orbit that much. Okay, so we're going to then draw a line from the center of the sun to where the planet is located right now, and I'll do my best job at doing that. And then I'll draw another line to where the planet is right now. Okay, and then this area here, we'll shade this in a little bit. Let's kind of do that. So this area is swept out in that certain time interval there. Now when it gets closer to the sun, okay, in order to have the same amount of area, it'll probably need to be around there and then maybe somewhere over here. Okay, now let me get my lines to draw. So I can go from the center of the sun to there, and the center of sun to here, and it works out pretty well. Okay, now let's take another marker here to kind of like shade that area in here. What this means is the area here has to equal the area here. So we're going to have probably slow motion from here to there, and then much faster motion as it goes around there when it gets closer to the sun. And that's kind of what that's about. Now what about this, you know, square of the period is proportional to the radius cube thing? Well, that comes from, you know, again, this equation here. We know that force centripetal has got to equal force gravity. So I'm going to do mv squared divided by r is equal to g little m big M divided by r squared. Okay, now let's clarify. We're now going to make the planet the little m, and we'll make the star a big M, because now the star is much bigger than the planet's mass usually. Okay, once again we can cancel this out. Okay, but I'm going to substitute something in here. So I'm going to say velocity is equal to 2 pi, okay, divided by time. Like that, right? Okay, but I'm going to add an r here. Okay, and I'm adding that r, okay, because I need circumference per time. Okay, back here, I see I can x out one of the r's here, and we're left with v squared is equal to gm, that's a big M, divided by r. Okay, so I'm doing circumference per time as this planet goes all the way around. Okay, I'm going to substitute this expression in where I see v squared. Okay, so then I have, and I'll write this over here, I'll have 2 pi r divided by time, and that's squared, equals gm divided by r. Okay, I'm going to square and then I'm going to crisscross to kind of save time. So I'm going to have, I'll write this down here, I'll have t squared g big M is equal to 4 pi squared r cubed. Okay, now if I divide both sides by gm, and I'm running out of room, so I'll put this here. So we have t squared is equal to 4 pi squared r cubed, okay, divided by g big M. Okay, so we see that the square of the period is directly proportional to the radius cubed. Now what we actually use for radius is an average distance from that planet to the sun. And we do that by averaging the semi-major axis and the semi-minor axis of the orbit. Now remember, the semi-major would be half the distance here, and the semi-major would be the half the distance there. Okay, and this is a useful equation. And again, if we see a planet going around a star, you know, we can use this because this M stands for the mass of the star. So if we know the time it takes for it to go around, and we know the average distance from that planet to the sun, we can calculate the mass of the sun. Okay, and that's it for the beginning part of rotational dynamics.